Welcome back to our adventures with polynomial functions. We are going to continue with our graphs. Oh, this is still red from my previous video, I guess. So we're going to continue with graphs of polynomial functions. So I'll probably name it part 2 in my titles. Okay, so in the last video, we went through all kinds of things about graphing polynomial functions. We started out with looking at some of the basic functions that we've learned, like linear function, the x squared, x cubed, x to the fourth, those kinds of functions, how they look, and some of their patterns to them. And then we dove deeper and we looked at the zeros of polynomial functions and their multiplicities, and what that means as far as behavior at zeros. And then we looked at also the end behaviors when we look at that leading or dominant term in the polynomial function. And we're able to decide, what's happening on the ends of the graph. And all kinds of stuff can be happening in the middle. And we graphed a few examples. Well, today I want to kind of go and reverse it first, before we talk about the intermediate value theorem and then boundedness theorem, and then maybe doing a nice little application type example, like word problem. Application is a fancy way of saying word problem. All right. What if what if you're given the function and you're also given what the graph looks like? I'm just going to do a rough sketch of this graph. I'm not going to be fancy and perfect. And then, looking at this graph, it's labeled so you know where the zeros are. And you're asked from that to factor f of x, given the function and given the graph. Well, now, you could go back and dig back and try to work with finding the zeros and working with those, but you don't have to, because it's already given to you in the graph. It's right there. They labeled them for you, so you know for the zeros, so you have an idea of what's going on there. You're looking at that function and you see that the leading term is a negative, so there needs to be a negative 1. All right, and then that you have some different zeros. Like a zero of -6 means you're going to have a factor of x plus 6. And notice that the graph goes right through that 0. So that tells us that the multiplicity should be around 1. Then at -1, you have a 0 there, so you're going to have a factor of x plus 1. Remember, the factor's the sign's opposite of the zero's sign. Because the factor equals 0, and then you get like x plus 1 equals 0, x equals -1. Anyways, you already know that. But notice the behavior of the graph at that 0. It comes up, hits the 0, bounces off, comes back down. So that tells us that we're dealing with a multiplicity that's an even number. And I'm going to go ahead and fill in a 2 right now, because I know that my final exponent in that leading term has to be a 5. So I'm just going to put a 2 for now and see what happens with that. Then at 3, I know I need an x minus 3 factor. Hey, it goes straight through, so I know that's an x minus 3 to the first power. And then same thing with 5, x minus 5 to the first power. It goes straight through there, so I know that's going to be just a multiplicity of 1. And looking at all those exponents, 1 plus 2 plus 1 plus 1, that'll add up to the 5 that we need in that leading term. And then we have that -1 out front for the negative. So now we're set. So the final factored version of f of x is -1 times x plus 6 times x plus 1 squared times x minus 3 times x minus 5. So there you go. There you have it. So that's not too bad, huh? Now this one wasn't too bad either because that leading term had a -1 for its coefficient. So when we went to factor, it's like, I just put a -1 out there. If it had something else, we could factor that out and then see, and then like consider that like your still has to be your A. The A goes out in the front there, so whatever that coefficient is. All right, what if we're given a little less information? What if we're still given the graph? Looks kind of like this. Just label some key points that they tell us. Okay, so they tell us that there's these two zeros, and they tell us what the y-intercept is. They want us to write the function of least degree. Okay, so we can start out, we don't necessarily know what A is right now, so we're going to have to find that. We don't know what that leading coefficient would be. But we do know from the zeros that we have to have factors x plus 5 for that 0 of -5 and x minus 3 for that 0 of 3. Now, since it says least degree, when we go to write our exponents, we can just go with the smallest one that fits the situation. Like going through the -5, that it goes straight through, so we know that's going to be a 1 anyways. There's not going to be another number there. But with a 3, it comes down to 3, bounces off, and goes back up. So that could be some kind of an even multiplicity. But since they say least degree, we'll go with that smallest number involved there, and that would be a 2. All right, so far so good. Now we don't know A, but since we know that y-intercept, we know that f at 0 equals 9, we can plug that in and solve for A. So we can do f at 0. We got A times 0 plus 5 times 0 minus 3 squared, and that has to equal 9. So A times 5 times 9 equals 9, because 0 plus 5 is 5, and then -3 squared would be 9. So 45A equals 9, which means A equals 1/5, because 9/45. So you could write f of x equals 1/5 times x plus 5 times x minus 3 squared. And I mean, there's your function. If you really want to, you can multiply all that out and write the function, multiply it out, and that works too. Just see what your directions say to do to decide. If it doesn't say, then it's perfectly fine to leave it in factored form like that. Now, if you do multiply it out, you'll find that your leading term, or dominant term, or whatever they want to call it, is 1/5 x cubed. So notice that your end behavior on your graph matches what's happening there. It's positive, and it's a cube, an odd degree bigger than 1. So that end behavior works. Like if you look at the fact that it's going down over here on the left and going up over here on the right, and then you got stuff going on in between. Let's do one more of those where you have to write the function of least degree. I think these are fun. It's kind of like trying to solve a mystery or something. Again, forgive my sketching here. This is supposed to be coming down and being tangent right there and going through. All right. So once again, we're going to use its graph, and we're going to write the function of least degree. So we can start with f of x equals, we don't know what A is yet, but we'll find it in a minute. Then that 0 of -1 means we can write x plus 1. And we can write that to the first power because the graph goes straight through there. And then that +1 means we can write x minus 1. But I try to draw it intentionally here, but notice it comes down and does that nice little wiggle where it goes tangent for a brief second and then continues on through. So that needs to be an odd degree, more than 1, or an odd exponent, odd degree. But we want least degree, so we're going to put a 3 there. We're just going to put the smallest possible. Now we know that f at 0 equals 2, so that's going to be valuable for trying to find a, find that leading coefficient. So f at 0, if we plug in 0, that has to equal 2. So a times 1 times -1 has to equal 2. So a has to equal -2. So f of x equals -2, that's that a, and then our x plus 1 factor and our x minus 1 cubed factor. The leading term, or the dominant term, if you multiply that out, would be -2x to the 4th. And notice the behavior here. The end behavior is what we expected. It's negative and it's an even power, so we expect the end behavior to be like that. And that's exactly what's happening in our function, in our graph. All right. Now let's jump into something called the intermediate value theorem. What does this say? If f of x is a polynomial, so we're doing all these polynomial functions, function with only real coefficients. So right now we're limiting to real coefficients, no imaginary. And if for real numbers a and b, the values f at a and f at b are opposite in sign, then there exists at least one real zero between a and b. Okay. Remember, this is an if-then statement. That's going to be important in a few minutes. I'm going to revisit that fact that it's an if-then statement. All right, so we're dealing with a polynomial function, just keeping it real, the coefficients. And we've got two values where when we plug them into this function, the two values come back opposite its sign. If this happens, then we know that between those two values, there's at least one real zero in there. So if you think about it, think about what's happening here. Like if you have a function that looks like this, and let's say that your a is here and your b is here, if you plug in a, you're going to get a nice negative number for your result. If you plug in b, you're going to get a nice positive number for your result. So this is telling us that, like, if you have these two real numbers, a and b, in this particular polynomial function, then when you plug in and you get those y values as your results, they're opposite in sign. So there has to be at least one real zero between those two values, and there is right here. So think about what's happening. It's crossing the x. At a zero, it's crossing the x, possibly crossing the x-axis. It could be bouncing, but it's possibly crossing. So if the signs are different, then it definitely crossed. Went from at least once. I mean, it might have crossed more than that. You could have had a situation like this, where your A is here and your B is here. So I mean, it's saying at least one. So there's that. But be careful. This is an if-then statement. It's a conditional statement. The inverse isn't necessarily true. This is a conditional. And if you took logic at some point, you learned that the conditional and the inverse are not logically equivalent. So if f of a and f of b not opposite, then not necessarily no zero between A and B. All right, let me see if I can sketch that real quickly right here. Let's say you have a graph that looks like this. And let's say your A is here and your B is here. So notice the sign of f at A and the sign of f at B are both negative. So f at A and f at B are not opposite, but notice there are still zeros in between. So just because they're not opposite, you can't conclude there's no zeros. But if they are opposite, you do know that there's at least one zero in between them. So that's what this intermediate value theorem is all about. All right, let's look at an example that, like in your book, what they might ask you to do with this. All right, for the intermediate value theorem, what they might say is, let's say you have the function f of x equals negative x, let me see here, negative x cubed plus 2x squared minus 4x plus 5. And they might say, use synthetic division and a graph to show that this function, the f, has a real zero between 1 and 2. We're talking real here. We're not worrying about the non-real. Okay, so what do we need to do? We basically need to find f at 1 and f at 2. And we need to look at their signs. And we can find f at 1 and f at 2 using the synthetic division that they're asking us to do here. So we can take our function, and okay, our coefficients are -1, 2, -4, and 5. We can go and divide by 1. And then that remainder tells us the answer. So f at 1 equals 2. And then we can take the same function and divide by 2. And then that remainder tells us the answer there. And the key is that the signs are different. The signs differ. So then that tells us that there's at least one real zero between 1 and 2, as long as those signs are different. And in fact, if you went ahead and graphed this, it would look something like this. I'm just doing a rough sketch, so it would go through 5 right there, and then actually the 0, you can put this function into Desmos, and then when you click on the graph, it'll put like in gray the key points, and then you can hover your mouse over them and see what the values are. So I found out that the 0 is around 1.526, 0. It's a nice little approximation. But notice that is indeed between 1 and 2, because your 1 would be, you know, somewhere over here, your 2 would be somewhere over there. So it does indeed have a 0 in between. All right, let's next talk about something called the boundedness theorem. So all of these things can help us when we're trying to find zeros and graph these functions. It can help us narrow things down faster. Boundedness theorem. All right, what does this say? Let f of x be a polynomial function again. Of degree n greater than or equal to 1, with real coefficients, so we're still focusing on real coefficients right now, and with a positive leading coefficient. So this boundedness theorem is very strict. Suppose f of x, so you're taking the function, is divided synthetically by x minus c. So usually c is a 0, and x minus c would be a factor. All right, A. If c is greater than 0, so positive, and all numbers in the bottom row in other words, the coefficients and the remainder of the synthetic division are non-negative, see, non-negative just means it can be 0 or positive. That's what they say when they say non-negative. When they're okay with including 0, they say non-negative. Then f of x has no 0 greater than z. All right, so basically if you do the synthetic division, if you take a c that's bigger than 0 and do the synthetic division with this polynomial function and get that your entire row with your quotient and remainder are non-negative, so 0 or positive, then that means you have there in your grasp the biggest 0 for the function, you know, assuming that the remainder is 0. I mean, if there's a different remainder, as long as there's not going to be a 0 bigger than that number. You could have a remainder other than 0. So I guess here they're not using c to necessarily be a 0. That's confusing. Anyways, okay. That's something to keep in mind. But key is looking at your signs, and then you're kind of narrowing down. Well, we know at this point that zeros can't be higher than this. It can be lower. But that is really confusing. C isn't necessarily a 0. All right, if C is less than 0, and the numbers in the bottom row of the synthetic division alternate in sign, with 0, positive or negative as needed. So if you need 0 to be a certain sign, make it that sign. Then f of x has no 0 less than c. I really wish they'd use something other than c there for that definition. Okay. Sometimes that's these books for you. So if you do the synthetic division with a number that's negative, and you find that that entire bottom row with your quotient and your remainder alternate sign, where if there's a 0 in there somewhere, you can make that sign what you want it to, what you need it to be, then that means that there's no 0 less than c. So no 0. So it helps create boundaries for, okay, we don't know where our zeros are, but we can figure out there's no zeros bigger than this and no zeros less than this. So it happens a lot. Like if you take calculus and on further, you're going to find that that's used a lot with narrowing down your boundaries and trying to say, well, in between these two values, we know it's going on in here. And that's actually even current proofs that mathematicians are working on, trying to prove one thing, maybe trying to prove something with infinity, but then narrowing it down and saying, well, we can prove for these that this value exists within these 200 values, or something like that. Quick little kind of a summary of the proof in your book on page 368. It's saying by the division algorithm, if you divide your function by x minus c, and you have a q of x, that's your quotient, and r, that's remainder, you've seen this before, then by the division algorithm, x minus c times q of x plus r is that function. In other words, in a division problem, you can take divisor times quotient plus remainder, and that equals your dividend. And that's, in a nutshell, what that's saying. For the part A, we have that c is bigger than 0. We know also the coefficients, we're talking about real coefficients, and we're talking about positive leading coefficient there. So all the coefficients of q of x are non-negative. By that part A, we're looking at the coefficients of the quotient are non-negative. Because remember, at the very bottom, when we finish the synthetic division, we're looking at if all those are non-negative, all those signs, and you know that your r, your remainder, is non-negative because, again, all those signs in the synthetic division are positive. You know that your c is bigger than 0 because, again, this is just part A's like layout of, all right, if these situations are occurring, then we can also look at, well, if x is greater than c, then x minus c is greater than 0. And we're going to use that to set up our conclusion about why this is true, why f of x would have no 0 greater than c. Well, if all of these things are happening, like let's say you had an x value that's bigger than c, then x minus c would be greater than 0. So if all of that happens, then your f of x has to be greater than 0. So f of x will never be 0 for x greater than c. So in other words, if all those requirements in part A are met, and you're evaluating some kind of domain value that's bigger than the c, and you consider that, then your f of x will always be positive. It can, whatever you're plugging in for x can not be another 0. So then you know that you've got your boundary. You've got your boundary for where zeros can't be bigger. And you can do something similar for part B in trying to show your boundary for where zeros can't be any smaller than this value. So those values aren't necessarily your zeros, but you've got your boundary now, marking it off. All right, what will your book ask you to do? It'll give you a function, x to the 4th plus 5x squared plus 3x minus 7. And it'll say to show that the real zeros of this function satisfy these conditions. Okay, so they might say something like no real 0 is greater than 1. All right, so 1 is that c value, that possible boundary. We're going to show that 1 is that boundary and that you can't have, your zeros can't be bigger than that. And 1's not necessarily a 0. In fact, when we do the division here, we're going to find out it's not. Here's a little quick reminder. It's so easy to forget when you're doing synthetic division to make sure to put in zeros for those missing terms. Like x to the 4th plus 5x squared skips right over the x cubed term. So make sure you put a 0 in there. I know I tend to forget. And one of these days I'm probably going to forget on video, and that's going to be terrible. But one of y'all can write me and say, hey, Miss Schofield. All right. So in fact, yeah, that 1 is not a 0 because the remainder is 2. But f at 1 equals 2. But anyways, but the fact that all of the signs there in that bottom row are non-negative. I don't see any negative signs there. Woo. 0 can be in there, but it's not, but it could be a problem, and that's fine. It's just you can't have any negatives. So since they're all non-negatives, then this proves it for us. Or part B, what about no real 0 is less than -2. All right, I'm running out of space. I really don't want to start fresh, so I'm just going to squeeze it in right here. All right, let's look at what's happening to the signs. Yeah, you go from positive to negative to positive to negative to positive. They alternate signs. So this proves there's no real 0 less than -2. So your real zeros, and then -2 is not a real 0 either, because look at the remainder being 23. You need 0 there for it to be a 0. But you know that the zeros, the real zeros, are bounded by -2 and 1. So if you have real zeros, they have to exist between those two values. Hence the boundedness theorem. All right. Let me conclude this video by doing an example of a word problem in the lesson. I just wanted to do it to point out a few things. You're going to find that the lesson asks you to do some approximating using a graphing calculator. You can go on Desmos. You're going to be allowed to use Desmos for parts of things. And you can graph the functions in there and then click on the graph and it'll highlight those zeros for you. So you don't have to necessarily learn how to use the graphing calculator to do it. If you do want to learn the graphing calculator, it's in your book. It tells you how to do it. But I wanted to do an application problem. It's actually similar to one of the homework problems involving finding volume of a box, where you have this rectangular piece of cardboard. And this particular one is 18 inches by 12 inches. So I'm taking this right out of the book. Page 375, number 91. But you're going to cut this cardboard so that you can create a box. You're going to cut corners and then fold up the flaps. So for now it's a topless box. So you're going to eliminate these corners so that you have a box. We don't know how big these corners are going to be, but we do know that they're squares. So the dimension, all four are the same sized square. So we'll just go ahead and call that dimension x. We don't know what it is yet. That's what we're trying to find. And then once we cut those squares out, we can fold along these dotted lines, fold it up, and make the little box shape and be open topped. All right, one of the first questions asked are, what are the restrictions on x? Well, if you look at the shorter side, the 12-inch side, x gets cut out twice. You can't have x getting cut out ever. It needs to be more than 0. So you're actually cutting something. But then it can't ever equal the 12 inches because then you would just be cutting off that whole length there. So x itself has to be less than 6 because x is doubled when you're cutting the squares. You don't want it to be 6 or higher because then you would be completely cutting off that side of the box, that piece of the box. And then next it wants you to think about a volume function, like what would be the volume of this box? Well, the volume of a box is length times width times height. So in our case, once we cut out those squares, the side that's 18 inches would be minus those 2 x's. The side that's 12 inches would be minus those 2 x's. And then the folded up sides would be have a height of x. And if you want, you can multiply all that out. Get this nice little volume function. 4x cubed minus 60x squared plus 216x. I'm not gonna, you can multiply that out on your own. If you get stuck, let me know. I'm glad to help you with that. All right, so then they go on and ask what value of x will give a maximum volume. And this is where the calculator comes in handy, because this is going to be kind of a, I mean, you could sit there and try to find it, but just use the calculator. If you go ahead and graph this lovely thing, It's a cubic. And in fact, this particular cubic has 3 real zeros, which you could probably see that right away with the factored version. So with the factored version, 18 minus 2x tells us that one of the zeros is 9. 12 minus 2x tells us that one of the zeros is 6. And then x tells us that one of the zeros is 0. Okay, but we're limiting ourselves to x being bigger than 0 and less than 6. So we're focusing on this piece right here. And that maximum value is right here. Again, if you put this into Desmos, it tells you those values. So like you can focus on that area, you can click on the graph. I'm doing it right now. Hovering my mouse, you can't see me, but I'm hovering my mouse, and it's telling me that that particular point has coordinates of 2.354, 148.162. So if you make your squares 2.354 inches in dimension, you will get the maximum volume of that box at 148, or 148.162. All right, what do we have to do next? Then I messed up. I had changed my graph earlier. I was like, no wonder that's not coming out right. I'm looking at my notes, and I had skipped ahead and done something else earlier for the next part, and so the graph wasn't giving me the exact value. I apologize for that. That's actually not 148.62. It's actually 228.162. It's like, why is that not matching? That makes a lot more sense. Okay. So yeah, the actual maximum volume would be the 228.16 cubic inches. So you want to make your x to be 2.354 inches, and then your volume would be 228.162 cubic inches. Okay, so then the graph change I had made is for the next part. For what value will the volume be greater than 80 cubic inches? So what I did is I thought about my volume function being greater than 80. So in my calculator, and this is why I messed up, I thought, well, if the volume is greater than 80, then I could go ahead and subtract 80 from that function and see what that graph looks like, see what's going on there. And keeping in mind that my x's still have to be between certain values. So graphing v minus 180, I asked myself, where is that v greater than 80? And when I looked at the graph, put a point there, I determined that my x's fell from 0.417 to 5 because of the way the graph, it has that little like hill. So for the greater than 80, it's limited to where that's happening. But adjusting the function allowed me to go in and play and see see what's going on there. Okay, so like a problem like that on your test, you'll be able to use the graphing Desmos for it. So just be familiar with how to use the graphing calculator in Desmos. It tells you a lot when you start clicking on everything, which is really nice. So there it is. Well, I hope you enjoyed. That wraps up your polynomial functions, and we will next time be getting into rational functions. Actually, those video links are already posted in your Canvas course, so enjoy those, and then eventually we'll come back and look at inequalities. So, all right, thank you for joining me.